All right, today we are going to tackle a question from the world of probability that trips up, well, pretty much everyone. What is the real deal with permutations and combinations? Let's get this sorted out, once and for all. Okay, so to get our heads around this, let's just jump right in with a little puzzle. Take a look at this. You've got 6 different letters. If you use each letter only one time, how many different 6-letter words can you possibly make? And yeah, we're using the term words very loosely here. Just take a second. What do you think? Any guess off the top of your head? Whoa, 720. Is that what you were expecting? It's way bigger than most people think, right? And that, right there, is exactly why we can't just sit here and list them all out. There's got to be a system, some method to the madness. So how on earth do we get to a number like 720? Well, that leads us right into our first big idea. So here's the secret. That puzzle, it was all about arrangements. The order of the letters is absolutely everything. You swap just 2 letters, and bam, you've got a brand new word. Let's break it down step by step. For that first slot in our word, we have all 6 letters to choose from, right? Easy enough. But once we've picked one, let's say we picked A. How many choices are left for the second spot? Well, only 5. And for the third spot? Now we're down to 4. You see where this is going? It just keeps going down until there's only 1 letter left for that very last spot. So to get the total number of possibilities, all we have to do is multiply those choices together. 6 times 5 times 4, all the way down to 1. And in the world of math, there's a super cool shorthand for this. It's called a factorial. We just write it as 6 with an exclamation mark. And when you punch that in, what do you get? Yep, 720. Okay, so this whole idea we've been playing with, it has an official name. It's called a permutation. And here's the one thing you absolutely have to remember about permutations. Order is critical. It matters. A, B, C, D, E, F is one unique arrangement, one permutation. But if you just swap those last 2 letters to get A, B, C, D, F, E, that's a totally different permutation. See? You know, the source material we're looking at really nailed it with this quote. It basically says however many ways you can arrange those 6 letters, that's how many words you can form. It's a perfect one-to-one match. Every new arrangement is a new word. All right, so that's pretty clear for arranging all 6 letters. But let's throw a little wrench in the works. What if you still have those same 6 letters, but now you only want to make a 4-letter word? Our simple 6 factorial trick isn't going to work anymore, is it? We need a better tool. And here it is, the big one. This is the general formula for permutations. You'll often see it as NPR. It's designed for exactly this kind of problem, figuring out how many ways you can arrange a smaller group of R items that you're picking from a bigger set of N. This is the elegant shortcut we were looking for. Okay, so I think we've got a pretty good grip on permutations, where order matters. But now, I want you to forget about that for a second. We're going to flip this whole thing on its head and ask a completely different kind of question. So, no more letters. Instead, imagine you've got 4 balls, each a different color: red, blue, green, yellow. And the question is super simple. How many different groups of 2 can you pick? And listen carefully to that key word. We're choosing a group, not arranging them. Now, with just 4 balls, we can actually just write them all down, right? You could have red and blue, or red and green, red and yellow, then blue and green, blue and yellow, and finally, green and yellow. That's it. 6 possible groups. Easy peasy. But you can probably see where this is going. This nice, simple method is about to become completely useless. Because what happens when we're not dealing with just 4 things? Yeah, we're now entering the world of combinations, and trust me, counting by hand is not an option. Let's just scale this up a bit. Instead of 4 balls, what if you have 100 balls in a bag, and you still just want to pick a group of 2? Could you list them all out? No way! You'd be writing for weeks. It's impossible. We absolutely need a formula for this. Okay, this right here, this is the absolute core of the whole thing. Let's really focus on this. With a permutation and arrangement, picking ball number 7 and then ball number 23 is one thing. Picking 23 and then 7 is a different thing. 2 outcomes. But when you're just making a group, who cares which one you picked first? The group with balls 7 and 23 is the exact same group, no matter how you picked them. This is the big idea, the aha moment that changes everything. So what does this mean? It means our permutation formula goes way overboard. It overcounts like crazy when all we want is a group. It counts the red, blue group, and the blue-red group as two separate things, but for us, it's just one group. So the fix has to be, we need to divide out all those extra redundant counts. And that is exactly what the combination formula does. You'll see it as NCR. And if you look closely, it's basically the permutation formula we just learned, but it has one extra little bit on the bottom. That R factorial, that's the magic key. It's the part that does the cleanup, dividing away all the duplicates, leaving us with just the pure number of unique groups. Whew, okay, we've been through a lot, so let's pause and bring this all home. The key takeaway, the big battle here, is arrangement versus selection. This table lays it out perfectly. Permutation. Order matters. The keyword is arrange. A phone password is the perfect example. 1234 is definitely not the same as 4321, right? One opens your phone, the other doesn't. Now combination. Order does not matter. The keywords are choose or group. And the classic example is pizza toppings. Who cares if you say pepperoni, mushroom, and onion, or onion, pepperoni, and mushroom? It's the same pizza. And you can see how the formulas are built around this exact difference. You know, there's a great line from the source material that says, "The magic of maths will speak for itself." And it's so true. Once you really get the why behind these formulas, they stop being just math, and they become these amazing tools for figuring things out. And I'll leave you with one last kind of funny thought to chew on. We just agreed pizza toppings are a combination. But what about a locker combination? To open a locker, the order of the numbers is everything, which means it's really a permutation. So why on earth do we all call it the wrong thing? Kind of weird, right? Something to think about. Thanks for tuning in.